All right, let's dive into something pretty crucial for understanding how these huge systems work. You
Mhm.
know, like these massive distributed systems we all rely on. Like, think about it. You've got like Amazon handling millions of transactions, Google serving up search results in a fraction of a second. It's all thanks to some really cleverly designed distributed systems. And right at the heart of these systems, we find the CAP theorem.
Yeah, the CAP theorem, it's one of those, well, it's one of those foundational ideas that once you grasp it, it kind of unlocks a whole new level of understanding. Like you
Yeah.
suddenly understand the choices and trade-offs involved in building,
Yeah.
reliable and scalable system.
Yeah, it's almost like it tells us, like, you can't have it all. You can only pick two out of three guarantees: consistency, availability, and partition tolerance.
Yeah.
It's almost like choosing your superpower combo. You know, what's most important for your particular mission?
And the really interesting part is that partition tolerance, the P in CAP, is pretty much non-negotiable. In a distributed system, network failures are just inevitable. Think of it like expecting some turbulence on a long flight. It's going to happen. You just got to be prepared for it.
Okay, so let's just break down these CIP guarantees. Starting with C, consistency. Our source material describes it as, well, it says every user sees the same data at the same time, regardless of which server they're connected to. So think of it like a global synchronized clock. Everyone sees the same time, no matter where they are.
Yeah, that's a really good way to visualize it. Strong consistency. It's vital in applications where, well, where discrepancies in data can
Yeah.
have some pretty serious consequences. Our sources point to financial systems as a prime example. Imagine if your bank account balance was inconsistent across different servers.
Chaos.
Right. You wouldn't want to see different balances in your like mobile banking app
Yeah.
and at the ATM. So in those cases, like consistency is king. But what about availability? Availability means the system is always up and running, ready to respond. Like think of those services you just expect to work, 24/7, like Netflix streaming or Google search. You want to watch that movie or find that answer, no matter what time it is.
So to stick with the financial analogy, if ATM availability is crucial, you might prioritize that over,
Over
in
consistency.
some scenarios, right?
Exactly. Our sources highlight how certain systems, like those handling online payments, they might temporarily sacrifice consistency during a network partition just to ensure the system remains operational. You might see a slightly delayed update on your balance, but at least the transaction goes through.
Makes sense. Now on to the P and CKP, partition tolerance. This is where things get really interesting. Our sources emphasize that in a distributed system, you simply can't avoid network failures. It's not a question of if they'll happen, but when.
Think of it like this. You have multiple servers spread across a network, and the connection between some of them gets disrupted. Partition tolerance just means the system continues to operate, even when those communication hiccups happen.
So it's about designing systems that, gracefully handle those inevitable network blips, just like a well-prepared ship can withstand a storm.
Hmm.
But if we always need partition tolerance, that means the real choice. It's between consistency and availability, right?
Precisely. You have to decide which trade-off makes more sense for your application, ensuring everyone always sees the same data, even if it means the system might become temporarily unavailable or prioritizing access, even if the data, might be slightly out of sync for a short period.
Yeah.
There is no right or wrong answer. It all depends on your specific needs and what you're willing to compromise on.
So you're saying that understanding the CIP theorem, it's less about finding like the perfect solution
Hmm.
and more about making like these informed choices based on the application you're building.
Yeah, absolutely. There's no one-size-fits-all answer here. It's all about understanding the trade-offs and aligning your system design with the priorities of your application.
I see, I see. Our source material has some great examples of how this plays out in real world systems. So let's start with those that prioritize consistency and availability, the CA systems. One that really stands out is a traditional banking system. Why is consistency so critical in that scenario?
Well, you got to think about the consequences of inconsistency in a banking system. Imagine like transferring money from one account to another, and the data, it doesn't update consistently across all servers. Suddenly you might see different balances, depending on which server you're connected to. That could lead to overdrafts, incorrect transactions, and a whole lot of confusion.
Yeah, that's a nightmare scenario. No wonder banks place such a high premium on on consistency. But as you mentioned earlier, the trade-off is, well, these systems might become unavailable during a network partition, right? To avoid showing that inconsistent data.
Exactly. Our sources, they point out that in a CA system, it's often better to have a temporary outage than to display potentially incorrect information. So like a safety mechanism to prevent bigger problems down the line. Okay, that makes sense. Let's move on to systems that prioritize availability and partition tolerance, the AP systems. Social media platforms are a great example here. Why is availability so crucial in that context?
Well, for social media platforms, it's all about keeping users engaged and connected. People expect to be able to scroll through their feeds, post updates, interact with others seamlessly. Even a brief outage can lead to, frustration and a perception that the platform is unreliable.
So to avoid those outages, these platforms are willing to sacrifice some consistency, right?
That's right. They might temporarily show you slightly outdated information if a network partition occurs. But the key is that you can still, you can still access and interact with the platform. Think about it. Would you rather see a slightly delayed post from a friend or have the entire platform crash?
I think we all know the answer to that one. Now for our final combination, consistency and partition tolerance, the CP systems. Our sources highlight examples like stock trading platforms and ticket booking systems. Why are these scenarios so sensitive to even the slightest inconsistency? Well, in these cases, even a small data discrepancy can have major consequences. Imagine like a stock trade executing twice because of inconsistent data. Or think about a ticket booking system overselling seats for a concert. Those errors could lead to financial losses, legal issues, damage to the system's reputation.
So in these high-stakes environments, it's better to have a temporary outage than to risk those potentially catastrophic inconsistencies.
Precisely. Our sources explain that CP systems prioritize data accuracy above all else. They'd rather become unavailable during a network partition than risk, displaying or processing inaccurate data. It's like pressing pause to make sure everything is perfectly in sync before resuming operations.
Now, our sources also mention that some modern databases, they're kind of blurring the lines between these CCAP combinations, offering more dynamic approaches. What's that all about?
It's fascinating how database technology is evolving. Traditionally, systems had to pick a fixed key combination and stick with it. But now we're seeing databases that can adapt their consistency and availability guarantees on the fly, depending on the those specific needs of the application.
So instead of being locked into a strict CA, AP, or CP choice, these databases can shift gears, dynamically adjust their priorities based on the situation.
Exactly. It's like having a car that can switch between different driving modes. Sport mode for speed, eco mode for efficiency, and off-road mode for rough terrain. These modern databases provide a level of flexibility that just wasn't possible before.
That's impressive. But I imagine it also adds a layer of complexity to the design and management of these systems.
There's definitely a trade-off. While this dynamic approach offers more flexibility, it also requires a deeper understanding of the underlying principles and careful consideration of the potential consequences. It's not a magic bullet, but it's a powerful tool in the hands of skilled engineers.
Okay, so we've explored these different CIP combinations, but our sources also touched on a concept called eventual consistency. What's the deal with that?
Eventual consistency is a fascinating concept that offers a more relaxed approach to data consistency, particularly in those AP systems where availability is paramount. Instead of demanding that all data be perfectly synchronized at all times, eventual consistency allows for lots of temporary inconsistencies with the guarantee that the data will eventually converge to a consistent state.
So it's like saying, hey, we might be a little out of sync for a moment, but don't worry, we'll all get on the same page eventually.
Exactly. It's a trade-off that makes sense in scenarios where occasional inconsistencies are acceptable and high availability is crucial. Think of things like social media feeds, content distribution networks, or collaborative editing tools. In these cases, eventual consistency allows the system to remain responsive and accessible even during network disruptions, while still striving for data consistency in the long run.
So if I see a slightly delayed update on my friend's latest post, or if my edits in a shared document take a moment to appear for others, that could be eventual consistency at work.
It very well could be. It's all about finding the right balance for the specific needs of the application. Eventual consistency can be a powerful tool for achieving both both high availability and a reasonable level of data consistency.
This whole discussion about the CAP theorem, it's making me realize just how much thought goes into designing these systems. These systems we often take for granted. It's like a hidden world of complexity and trade-offs.
It really is. And the beauty of the CAP theorem is that it provides a framework for navigating that complexity and making informed decisions about how to build reliable, scalable, and fit-for-purpose systems.
So to sum it all up, the CAP theorem, it's like a roadmap for building distributed systems. It helps us understand the trade-offs, make informed choices, and ultimately design systems that meet the specific needs of our applications.
And remember, there's no single right answer. It's all about choosing the right superpower combo for your particular mission, whether you prioritize consistency, availability, or a blend of both. The key is to understand the implications of your choices and design your system accordingly.
Well said. Now, for our listeners out there, I have a question for you. We've talked a lot about the trade-offs between consistency and availability, but what about the trade-offs associated with eventual consistency? What are the potential downsides or limitations of this approach? And in what scenarios might it not be the best fit? Something to ponder as we wrap up our deep dive into the CAP theorem. Okay, so as we wrap up our deep dive into the CAP theorem, let's just take a moment to reflect on what we've learned.
Yeah, we started by acknowledging that distributed systems, they're inherently complex, with multiple servers all working together across, these networks.
Yeah.
Networks that can and often do experience disruptions.
Right, and it's within the environment of complexity that the CAP theorem it shines a light. It guides us through those critical decisions that we face when designing these systems.
Yeah, and the beauty of the NEAP theorem is that it simplifies those decisions into this clear framework. It tells us we can only pick 2 out of 3 guarantees: consistency, availability, and partition tolerance. And since partition tolerance is, it's essential in a distributed world, the real choice, it boils down to consistency versus availability.
So we explored how different systems, they prioritize these guarantees based on their specific needs and the potential consequences of, inconsistency or unavailability.
We saw how, traditional banking systems, they really value consistency, even at the cost of temporary unavailability during those network disruptions, to ensure the accuracy of that, of that financial data.
Right. On the other hand, we have social media platforms. They prioritize availability, and they kind of accept the possibility of, slightly outdated information just to keep users connected and engaged.
And then there are those mission-critical systems, like stock trading platforms or ticket booking systems. They demand strict consistency. They opt for temporary outages rather than risk the potentially catastrophic consequences of inconsistent data.
But it's not just about picking a CK combination and sticking with it, right? We also discussed how modern databases are. They're kind of blurring the lines. They offer more dynamic approaches.
Right, approaches that can adapt to changing conditions.
Yeah.
And adjust their priorities on the fly.
And that dynamic approach, it brings a new level of flexibility, but it also demands a deeper understanding of the trade-offs involved.
Absolutely.
And finally, we touched on the concept of eventual consistency, which is a more relaxed approach that embraces the reality of, of temporary inconsistencies in exchange for that high availability.
And eventual consistency can be a really powerful strategy in systems where those occasional discrepancies are acceptable.
Yeah.
But it's important to be aware of its limitations and potential downsides.
So as you navigate the world of distributed systems, remember the key takeaway from this deep dive. There's no one-size-fits-all solution.
Yeah, the CAP theorem, it isn't about finding the perfect answer. It's about making those informed choices, understanding the trade-offs, and designing systems that really align with, with the specific needs and priorities of your applications.
Think of it as a mental model, a tool for navigating that complexity and guiding you towards building robust, scalable, and reliable systems.
And with that, we'll leave you with this final thought. As you continue to explore the world of distributed systems, challenge yourself to go beyond the basics. Dig deeper into the nuances of the CAP theorem. Consider the trade-offs associated with those different consistency models, and explore how emerging technologies are kind of pushing the boundaries of what's possible.
Go forth armed with the knowledge and insights we've shared, and continue to dive deep into this fascinating world of distributed systems.